The purpose of this video is to introduce you to a tank circuit used as a bandpass filter to tune a radio from one frequency to the other when receiving. It involves some understanding of resonance. So if you don't know what resonance is, see my video, Basic Electricity Part 12, Resonance Explained, and that will help you a lot in understanding this video. Now, a tank circuit is made up of three parts: a capacitor, an inductor, and a resistor. The input would be an antenna. The important part to understand about resonance is that the reactances of the capacitor and the inductor work opposite each other. And all reactance is a complex resistance brought on by the components, how they react to AC. The important part is that the reactances from an inductor and a capacitor are 180 degrees out of phase. And at the same amplitude, they will cancel each other. They cancel each other out, so there's nothing left but the circuit's inherent resistance and the resistor that you've installed. So when we design a circuit, a tank circuit, we want our reactances to be equal. So let's take a look at what we want to receive. We should, for our first project, if you're just looking into this on how to build a receiver or how a receiver works, you're going to want to, and you're going to make a receiver, you're going to want to pick a band, a radio frequency band, rich in a lot of different sources of radio frequencies. The best one would be the standard AM broadcast band, and that's what we'll use. It runs from 350 kilohertz to 1,700 kilohertz, or about 1.7 megahertz. So we want our bandpass filter and our tank circuit to be midpoint or thereabouts of that band, somewhere near the midpoint, so we can tune either side up and down the band. And the midpoint here is 1,020 kilohertz or thereabouts, close enough, or 1.02 megahertz. So if we want to choose components, that will make the midpoint of our filter equal to the midpoint of the standard AM broadcast band. So in this diagram we see kind of how it works. You see all that rainbow multicolored radio waves off to the left. Those are all the radio waves. Your antenna does not select radio waves. Very broadly it will, but that's a whole nother topic on how antennas work. Essentially, they receive everything in the RF spectrum. Those frequencies go into the tank circuit. Then you set the components. The XC is the capacitive reactance. The XL is the inductive reactance. You set your bandwidth with that resistor. We want it in the middle at 1020 kilohertz because anything that's 70.7% below the maximum on that curve, which is the middle of our band, that 1020 kilohertz, 70% below that will not pass through the filter. It will be rejected. It'll be blocked because it's not going to be resonant enough to make it through the filter. So then that top part, the purple part, the band pass, those frequencies go through the output of the circuit to get amplified if you have if you're going to amplify them, and then into the speaker or the earpiece. And we set that band pass at about 10 kilohertz wide. That is the band width. The reason we do that is because the FCC set it up so any radio stations in a proximity where they can be received need to be 10 kilohertz apart so they don't interfere with each other. And then this diagram just shows the pass band going through the output. The rest is rejected. It makes it out. So we need to figure out what our components need to be. To do that, we're going to pick a capacitor. The reason we're picking the capacitor first is because they come in a lot of variety of standard values. Their value for a capacitor is measured in farads, or a sub-measurement like picofarads, microfarads, nanofarads. So we're going to pick one of these capacitors. We'll pick the disc capacitor in the middle, and then we'll go and pick a coil. These are good coils to pick. They come out of radios, so they would make it real easy to tune to the coil. So there's our coil. They are measured in henries. So once we get that, we can go about calculating what we need in this circuit to get to that center frequency of 1020 kilohertz. There's a mathematical formula for that, or you can use an app, which is what I do. And I'll show you how to do it as we go along. We're using a nano VNA, and we have calibrated our nano VNA for the AM band, 350 kilohertz to 1700 kilohertz, or 1.7 megahertz. We need this set to our target frequency, which was 1020 kilohertz, or 1.020 megahertz. We can't get to 1.020. The closest we can get is to 1.025. That will be close enough. Now we have found a coil. I took this out of an AM radio. It makes it real handy. It has 3 leads. It has a little tan one down here. It has a black one here. Has another black one here. We're going to measure, put our red one on this black one here. Doesn't matter. I'm just going to do that arbitrarily. And then we're going to put this on there. That gives us a reading of 451 microhenries. That is its inductance. Now we'll put it on the other black lead, and that gives us 420 microhenries. Now we switch it from the tan one to both black ones, and that's 3.44 microhenries. Now with these components, you will be on that 1020 kilohertz target frequency, but the problem is you won't be able to tune the circuit. If you want to change frequencies, you have to change one or the other of these two components, which is very unhandy. So what you'd really want to do is change one of these components out with another component, another capacitor, called a variable capacitor. This capacitor has a shaft on it that you can turn, and it varies its range. So we'll use this. It has some wording on the back of it that I could look up a data sheet on this and find out what its capacitive values are. And I did look it up. And I didn't have anything. It didn't show me anything on its range. We're going to measure the capacitance value of it. It's the halfway between the two that we're most interested, the mid-range. Now we'll get it at the mid-range. The way I'm going to do the mid-range is we have it all the way this way. That diagonal, that little flat spot, is at this corner. If I turn it this way, it's at this corner. So I'm going to turn it halfway between the two, so that flat spot is at this corner up here. We'll hook him back up, and we'll go with 142 picofarads. Okay, so we're ready to take our numbers we have and plug them into a calculator to see what works for our center frequency. You can use a formula and you can use an app. There's several apps. I'm going to use this app called ElectroDoc, and I don't have any financial ties to this or anything. I'm not a sponsor or anything. I just happen to use this one and I like it. There are others out there. So, it has a whole bunch of things that you can do with it. We're going to use reactance resonance. So we're ready to enter our numbers that we got. So we'll start with our capacitance of 142 picofarads. Then, doesn't matter what we're going to calculate right now because we have to put in other stuff. We'll put our frequency in at 1.02 megahertz. And we're going to calculate for L because we know what C is. Our L needs to be 171.456 microhenries. If we look on our list of numbers, we don't have anything near that. So we got a problem. So what are we going to do? We're going to have to find out. Let's put in our microhenries here. 451 microhenries, and we're going to solve for C. So we came up with 53 picofarads. We don't have 53 picofarads. So we have a problem. Let's put a number in that we do. 142 picofarads. Solve for frequency. Yeah, it's not even close to where we need to be. So we need a different capacitor or a different inductor. I want to choose the same inductor because it came out of a radio. We're going to see if we can find a capacitor to get the capacitance we need. So is what we have done. We have found a capacitor and we've checked for its capacitance, and it comes out at 91.8. So we want to combine two capacitors, our variable capacitor and our 91.8 picofarad capacitor, and see if we come out with our 53.9 picofarad capacitor that we need to make this work. So we're going to combine them in series. When you do that, this formula shows you how that works. But I'm going to use the app. Go into capacitors in series parallel. We want to set, we have a little setting down here that says put it at C1 series. 142, that's picofarads. So with the 142 variable capacitor that we have, so what happens if we do a 91.8? We get 55 picofarads. That may be close enough. Let's go back and try it. So we're dealing with a 55. It's only 2 off. 55.7 picofarads is what we should end up with. And let's see what happens when we go back to our resonance. We have a inductor of 451. We have a capacitor at 55.7, and we want to calculate for frequency. That is pretty close. 1.004 with the numbers we have. So let's put up our capacitor, our variable capacitor, with this small capacitor soldered to it, like so. That's with the added capacitor. And measure the midpoint. Now, here we have it at middle range, and it's 58.1 picofarads. So now all we have to do is put those in our calculator, and that should take care of it. But we do have another option on our inductor to do 420 microhenries. We can try to be a little more careful on our center setting of the variable capacitor, and we came up with 58.1 picofarads. Plug that into our calculator and see if we're closer on the frequencies. And we have 1019 megahertz. So that is it. We hit our target. I showed you how to try and figure it out, and there it is. Now all we have to do is see what we need for our resistor to raise the Q, which is the selectivity of it. Okay, so we want to know the bandwidth of our tank circuit. So we know that the center frequency, which is 1020 kilohertz, and we know from our chart that the AM broadcast band is from 30 kilohertz to 1700 kilohertz. Our center frequency is 1020 kilohertz. So we know that any frequency below 70.7%, or mid-frequency, is going to get rejected by the tank circuit. So if we take our 1020 frequency, multiply it by 0.07, or 0.707, we get 721.4 megahertz. If you subtract that from our 1020, you get 299 kilohertz. If you add it to our 1020, you'll get 17.41 kilohertz. So our bandwidth is from 299 to 1741 kilohertz. And if you look at our chart, you'll see that it's bigger than the AM broadcast band, which is fine. We'll cover the whole AM broadcast band with this circuit. The issue is, with all of those stations being accepted into there at once, it'll sound like a room full of people yammering. You won't be able to pick out one station from the other. So, if you remember earlier in the video, we talked about a resistor, an R, which can narrow the bandwidth, raise the Q. That's the selectivity of the circuit. You would be able to narrow that down. The FCC said each station can only take up 10 kilohertz of bandwidth, and they're 10 kilohertz spaced apart. So we need to make our tank circuit have a bandwidth of 10 kilohertz. So we need to calculate what our R is. And on the internet, we have this calculator. So we're going to poke in our 58.1 picofarads. Our inductance was 420. We don't know our resistance, or if we don't know it, we can't put it in. But this gives us a center frequency of 1000 or 1018.1 kilohertz. We know our bandwidth is 10 kilohertz. We poke that in, it calculates the 26.39. We don't need to worry about the damping ratio. This gives us our Q factor. We're interested in the resistor value. And you could vary that. You could go up, let's say, what happens if our resistor is 30 ohms. 30 ohms. And it's 11 kilohertz wide. That ain't going to hurt anything. If you went, it was 26, what if you went down to 21? It's 7 kilohertz. That may make a difference. And it may cause distortion if their bandwidth is 10 kilohertz. So it's best to stick with the 26, whatever it was. Let's just poke our 10 kilohertz in there with our 26 about there. Get it as close as you can, 26, 27, 25, 26, 27 would work. And that's how you do it. So thank you for listening to the video. I hope it was useful. Please give me a like and a subscribe if you like this video, if you found it useful. Thanks again.